There, this is Anmashi Meroda from Group SWML 13, and we are handling a project that's about malaria drug resistance in HIV positive patients. So our keywords are malaria, HIV, anti-malaria treatment, genomics, biomedical markers, and many others ones. So the contents of our presentation are the introduction, related works, problem statement, research questions, down through the references. So when we come to the background and introduction, we're saying that we're going to use a predictive risk scoring model to determine the clinical staging. And in this, we're going to be using biomarker data from our data set. But then we see that 70% of our data set is actually unlabeled. So that means that very many supervised models are not going to be able to help us a lot here. That's why we're going to go for semi-supervised learning to address this. And then we say that we are going to work with low dimensional but high variance tabular biomarker data. And this method, if you use deep learning, it's not going to help us because deep learning usually overfits. And so instead of learning from the data, it's going to just memorize it. Yeah, so that's why we are still going with our semi-supervised learning. And then we're going to apply an iterative pseudo-label propagation to improve learning from unlabeled samples. What this means is that we're going to use the labeled data that we have first, the very few data, the 25%. And then after the model is trained on that, we are going to use that small data to now predict the unlabeled ones, right? So this small data that we use is going to create pseudo labels for the unlabeled, and then we keep training like that. So that's why we call it iterative. And then we're saying that it's designed with high interpretability and strict clinical risk constraints. And this means that instead of giving clinicians or doctors just a predictive score of which patient is at risk, maybe you say they are 75% at risk, instead of just giving them a score, we are going to interpret and explain how the score comes about, which feature contributes the most. Is it the varying genomics of the species, or is it the geographical background and all that? Yes, so we're going to be using also tree-based ensemble models like XG boosting, where you're going to have very many trees contributing to the learning of the model. And also the importance of this XG boost is that you get that feature contribution that we talked about. Yes, so the anti-malaria treatment failure prediction is difficult in resource-limited clinics due to scarcity of labeled clinical data. So we see that the scarcity of labeled data is a major challenge in our project. And then we talked about deep learning models, which are going to overfit this data set. And then the tree-based ensembles like XGBoost. And then we're going to combine these models with semi-supervised learning, and we utilize the unlabeled patient data and reduce the labeling problem. And then the interpretability part, which I already talked about. So when we come to the related work or the literature review, we're saying that current studies show a high burden of malaria and HIV co-infection in the sub-Saharan parts of Africa. This means that these two diseases interact with each other in a human system. So when an HIV patient has malaria, it means the HIV is going to reduce the immunity, or it's going to compromise the immunity of that person. And so when it compromises the immunity, it gives an opportunity for all other infections to come into the system. So that is where also malaria comes in. Now, when malaria and HIV combine, we see that there's a very high immunity suppression in just one system. So this HIV, the way it suppresses the immunity is by lowering the CD4 of that system. And so we see that this CD4 is a very important biomarker of our data set. So it's going to be part of our model to predict the risk of this patient. And so we see that these patients are taking ACTs because they have the malaria infection. These are artemisinin combined therapy. So we have artemether, and DP, and they are both effective, but then we see that DP has a lower rate of failing in patients. And then in combination to the ACTs, these patients are also taking ARTs. These ones are the antiretroviral therapies. And so when these two classes of ACTs and ARTs combine in one body system, they affect how the treatment is going to be effective in curing this patient or in improving their immunity and causing them to heal and therefore reducing their failure rate. So the ACTs and ARTs are very important to our data and to our model. And then we also see that there is, in Uganda specifically, this high prevalence of malaria alongside with HIV is concentrated in rural Ugandan parts. Yeah. Yeah. But the challenge that we face is that there is severe labor sparsity and the mathematical risk of manifold distortion during imputation. So the two main things we're looking at here are the labor sparsity and the mathematical risk of manifold distortion. So labor sparsity is how the labels are majorly they are not equally distributed, is what I can say. We have 75% of unlabeled data and we have 25% of labeled data. So if we were to use supervised learning, these models would catastrophically fail. So that's why we need semi-supervised learning, and in that we need to incorporate pseudo-label propagation so that our model can learn on the minority of the data that we have, and then use that for the majority that we don't have. But then for it to do this pseudo-label propagation, it needs to know how the data is structured, and that is the manifold distortion. It needs to know how the data is distributed, what is the shape of the data that we are working with. So that's why we are saying here that the input geometry is a highly incomplete tabular data set characterized by a 75% absence of ground truth of World Health Organization clinical stage labels. So that means that in every four, in every five patients, there is only one who is. In every four patients, there is one patient who has a true diagnosis of their disease. And we see that that's a very risky thing, especially for supervised models, because these ones are going to just drop the data instead of using it to learn. Well, when you go to the symptoms, we see that when we apply the naive approach, we call it the naive because it's the most common used approach for a very wide missing data. So this naive approach is that wherever there is missing data, you just get the global median or the global mean and you impute that value to that data. But then we see that this makes the feature space that artificially collapse because when you apply dimensionality reduction like PCA, these things are going to fail. And when you also apply pseudo label propagation on that distorted data, it is going to fail because you're going to have a very large cluster at the center because most of the data has that mean, and therefore you're going to find that you're going to have a patient who has an average in that centered cluster, but then in reality they don't exist. So you're literally giving clinicians and doctors fake data. And so this can cause very catastrophic results in the real world. So that's why you see that even you can see that since at first we had the high majority group and low majority group, we're going to see that now we can differentiate them because of the median and the mean imputation, the naive approach. Yes. So that is our that those were part of when we come to the when and why, we are saying that this optimization failure occurs because median imputation destroys the truth of logical manifold, as we've seen earlier in the symptoms. So this forces the semi-supervised algorithm to interpolate across an artificial dense center. So the center that is created after this global imputation of mean and median becomes artificial because we are putting unreal patients in, and we are giving them um, an average data that is not real, so it becomes artificial. And so we're saying that the solution to this can be deploying a robust multivariate iterative imputation. For example, when you use Miss Forest, because this one preserves the distribution or the relationship between the different features simultaneously. So it doesn't really cause a very high distortion or a very big distortion in the data that it assigns these missing values. So without that, the semi-supervised architecture will actually propagate a bias and therefore rendering the resulting risk scores to be clinically unsafe. Research questions and objectives. We have to determine the correlation between silicosis and the failure risk, we want to see if because the CD4 count represents the immunity. So we want to see if the immunity is going down, if the anti-malaria treatment failure is going up. Then we want to identify the specific anti-malaria drug treatment with the highest effectiveness across different HIV immune titers. So these patients are taking ACTs, the artemisinin-based combined therapies. It means they are on different medications. So we want to see which one has the highest effectiveness rate and which one causes the highest failure rate. Then we want to map geographical regions where HIV prevalence and anti-malaria drug resistance mostly overlap, meaning that we want to see if we are seeing a very high treatment failure rate in a certain geographical location, do other factors that are geographical affect that failure rate? Then also want to determine if patients with weak immune systems need to be moved more quickly to stronger backup treatments, and this will be determined by our predictive score. For the research contributions and outputs, we developed a predictive failure risk score that integrates the CD4 count with regional resistance markers so that we can quantify how specific immune titers directly correlate with anti-malarial treatment failure. So that we see that if your immunity is this, how does that affect how the medicine is going to either heal you or going to fail? Then we built a drug effectiveness mapping tool that identifies which ACT maintains the highest clearance rates in the presence of HIV-related immunosuppression. So we're saying that if you're on ACTs and you have HIV, we want a tool that will map how that drug will be effective in your system. Then we mapped high-risk overlap zones by linking regional HIV prevalence with localized data on these specific drugs so that we can specify where clinicians face the highest problems. Then lastly, we proposed a system to help HIV positive patients to get the right medicine faster. For the methodology and system architecture, we are going to use a self-training tree ensemble to utilize the 75% unlabeled patient data so that we use the labeled data to train on the unlabeled one. Then you're saying since random forest probabilities are unreliable, a probability calibration step is applied using isotonic regression. Calibration aligns predicted probabilities with true class frequencies before pseudo labels. And during training, only high confidence predictions above a strict threshold are converted into pseudo labels. And then these pseudo labeled samples are then added back into the training set iteratively. So that's what we were talking about earlier, that you get the labeled ones and then you use them as pseudos for the unlabeled ones, and then you do that iteratively. So we're saying that this approach reduces error propagation and prevents the model from making overconfident predictions on uncertain clinical cases. Yes.
Hello everyone, my name is Aruho Prisla and I will be taking us through the dataset description and the exploratory data analysis. So our dataset contains hematological biomarkers, that is the CD4 count, the hemoglobin, and the white blood cell count that are used to predict the World Health Organization HIV clinical stages. So about 75% of this data is unlabeled, making standard random chain splits unreliable. Evaluating this data on pseudo-labeled data can cause confirmation bias and overestimate model performance. A ground truth test split is used for reliable evaluation, and 20% of the test set includes only the physician labeled records with verified World Health Organization stages. The remaining labeled and all unlabeled data are used for semi-supervised training, as we shall see with the models. This ensures the evaluation reflects the real clinical reliability and not model self-agreement. So our data sets are dealing with, our data set that we merged deals with 3 different data sets that we merged to give us this information, which is a PF8 malaria gene dataset, an IDH dataset that is specifically for HIV, and an MTM shape dataset that contains malaria information from different countries. Our merged dataset leads us to the visualizations of our dataset. We have different visualizations that are plotted with different factors, the impact of immune titer against the anti-malaria failure risk, the relationship between the current CD4 count against the failure risk score, We have a heat map of failure risk score by immune tier and host stages, and many other different visualizations. There are so many, we may not be able to go through each of them one by one, but we are going to go through some of them. Number one, we are looking at this box plot of our immune tier, our failure risk score against immune tier. Our immune tier is the mild, the moderate, and the severe. And here we observe that patients in the severe immunosuppression have a high risk of failure, to react to the anti-malarial treatment. Then we also look at the relationship between the current CD4 count and the failure risk score, which is a plot of the failure risk score against the current CD4. This shows a downward trend that as our failure risk score, our current CD4 increases, our failure risk score decreases. Then we also look at the heat map, which is a failure risk score by immune tier against the host stages. Our heat map shows the average failure risk across combinations of immune tier and host stages. The darker cells represent a higher risk, and we see that patients who are both severely immunocompromised and advanced host stages have the highest predicted failure risk. Then we also look at the density of treatment failure that visualizes why severe moderate tiers need a faster triage. Then we also look at the hemoglobin, white blood cell, the CD4 count, all these against failure risk score, and also the host stages. We also look at the regional baseline against failure risk score, how patients in every region react to treatment, and how many failures in treatment we are going to see per region are all shown in all these plots. So in these plots, we are going to observe that our visual analytics show that immune suppression meaningfully increases malaria treatment failure risk, especially in high resistance regions, as we are going to as we have seen in the regional failure baselines. And we also see that clinicians should consider immune status when selecting anti-malarial therapy. For high-risk HIV patients should be given the faster malaria treatment to avoid very high failure risk scores. Thank you so much.
Hello everyone, this is Arija Docas taking you through the semi-supervised learning. We shall be focusing on the graphs in the semi-supervised learning section. So these graphs are meant to show how the model improves as it learns from the both labeled and unlabeled data. Starting with the first graph, this graph typically shows the model performance across the iterations of training. On the x-axis, we have the training iterations or the steps. On the y-axis, we have the performance metrics such as the accuracy or confidence. At the beginning, the model is trained only on the small label dataset, so the performance is relatively low. As we move along the graph, the model begins to assign the pseudolabels to unlabeled data. Only high confidence predictions are selected. These are added back into the training set. So you will notice the gradual increase in the performance, which indicates that the model is successfully learning from the additional data without being explicitly given labels. In the graph, if the graph stabilizes, it shows that the model has converged, meaning further iterations are not significantly improving the performance. The next graph shows the confidence or the probability distribution. This graph illustrates how confident the model is in its predictions. Initially, the predictions are uncertain, so probabilities are spread out. After calibration and training, predictions become more peaked, meaning the model is more confident. This is important because we only accept the pseudo labels when the model is highly confident, and this reduces the risk of introducing incorrect labels into the dataset. So this graph demonstrates that confidence improves over time, which validates the pseudo labeling strategy. Another important graph shows the effect of the probability calibration. Since the tree-based models like the random forest can produce the poorly calibrated probabilities, we apply the isotonic regression. So in this graph, before calibration, predicted probabilities may not match the actual outcomes. After calibration, the predictions align more closely with true class frequencies. So if the model predicts 70% probability, it should actually be correct about 70% of the time. This graph proves that our model's outputs are reliable and interpretable, which is very important in the medical decision making. Then we may also have maybe a graph showing the labeled and versus the pseudo-labeled data growth. This graph shows how the dataset evolves during training. Initially, only 25% is labeled. Over time, more unlabeled data is converted into pseudo-labeled data. You will see a steady increase in the amount of training data, which helps the model to learn better patterns. However, the growth is controlled. Only high confidence samples are added, preventing noise. Now moving forward from the graphs, these graphs collectively demonstrate that the model is learning effectively from the enabled data. Confidence and performance are improving over time, and the pseudo-labeling process is stable and controlled. Now moving to the conclusions and limitations. One key limitation is that the model still depends on the initial labeled data. So if this data is biased, the model may carry that bias forward during the pseudo-labeling. There is also a risk that the model may not generalize well to new or unseen populations. To address this, we ensured strict reproducibility, transparent methodology, and evaluation using only the ground truth labeled data. In conclusion, this approach successfully uses semi-supervised learning to overcome the label scarcity, improve prediction accuracy, and maintain clinical reliability. It provides a practical and scalable solution for resource-limited healthcare settings. Finally, the next steps we plan to validate on newer datasets include genomic markers and further improve the model. We also recommend focusing on high-risk patients, improving feature engineering, and integrating the model into the clinical decision systems. Thank you for listening. This is all we had.